everyone, and welcome to Chapter 3 of the Joy of Abstraction book club. As you can see, I'm in a different place today. This is my piano studio. This is my beloved piano, and it's been a bit of a day, I will admit. So I've got my glass of wine here. Cheers, everyone. You can hear the sound of the L because this building is very near the L. We've got some very interesting questions today, so thank you very much for that. And they're on my screen, so I've got to flip to my other screen to see what the first question is. We got a very broad question here about abstraction in general, and about how in the sciences, when we take an abstract view of a collection of phenomena, we sometimes develop important new ideas, such as an abstract view of relationships between animals. You might end up with the theory of evolution by natural selection. And does something similar happen with category theory? And I think, yes, that's the whole point, that finding abstract connections between anything in any field is likely to lead to deeper understanding and new ideas, where you can treat many things in the same way that you couldn't previously do. And the fact that category theory does that for mathematics means that, well, one of the things I really like about it is it means that the new thing that you make is itself a piece of mathematics. And that means that you can use the thing you made to study the thing that you made. And that does sound a bit circular, but it's one of the things I really like about it. And there's a lot of mathematics develops by making bridges between different fields, actually. And sometimes those are the big leaps forward in math. It's not just solving one problem in one field, but it's often the way that the problem was solved was by making a connection with a different field, or just the act of making that connection. So as I understand it, the proof, Andrew Wiles's proof of Fermat's last theorem, one of the things that was great about it wasn't just it, but it was the amount of theory that it used, making connections with things that maybe previously hadn't been thought of. And the contemporary fields of mathematics often have two words in them, right? That you may think of algebra or geometry or topology, but contemporary math has things like algebraic geometry and algebraic topology and geometric topology and algebraic number theory and things like that. And that's because the big advances have involved making connection between one field and another. And category theory has really helped with making those connections and putting them in a framework that can be made very rigorous and that can be made very general. And I'm speaking rather generally now because applications of category theory is definitely not my speciality. And so there are definitely other people who could speak more fluently and in more depth about the advances that have happened thanks to category theory. But it definitely makes for a very smooth framework for making those bridges between things. And that's one of the things that I really like about it. And I think that's one of the reasons that category theory quite rapidly became embedded in mathematics at a research level before it started being able to reach out even beyond mathematics and beyond math-related subjects, because then it went into physics and computer science and into way more things. Oh, there goes my elbow on my pencil. The next question is also a general question, that the ability of category theory to take an abstract view of anything seems to be similar to the function of intelligence. And does category theory have anything to teach us about what intelligence is, or how our intelligence may be artificially created? Now, I do think that category theory is being used in artificial intelligence, and I think that that's one of the things that the Topos Institute has been developing. So thanks, Topos Institute. I forgot to begin by thanking anyone. Oh no, I broke one of my golden rules. Thank you all for being here, and thank you to the Topos Institute for doing this. And does category theory have anything to tell us about what intelligence is? it's an interesting question, because I think really it's up to each of us to say what we think intelligence is. And personally, I do think that intelligence, well, deep down, I think intelligence is about how much you figure out how to help other people in the world, actually. But in terms of intellectual intelligence, I might say that the kind of intelligence that interests me is the kind where you are able to make connections between things and are able to cut through surface details to see deep connections between things, which is nothing against people who have the ability to work with immense quantities of detail. But the things I find interesting are seeing the broad structure. And of course, that's why I'm a category theorist. Or maybe I find it interesting because I'm a category theorist. No, I think that I found it interesting first, and that's why category theory always really appealed to me. And it interested me because I really, really am fascinated by that kind of intelligence, I think. I love talking to people about things that remind us of other things. When a book reminds you of another book, or a piece of music reminds you of another piece of music, or a person reminds you of another person, or a situation reminds you of another situation. And I think that that's a very important part of human intelligence. Whether category theory can tell us that or not, I think is more in doubt. I think that category theory can highlight things like that. And it has helped me, that understanding category theory has helped me to articulate the fact that I like that form of intelligence. But that's just a personal taste, and I wouldn't dream of saying that I think that that somehow is what intelligence is. I don't think I know what intelligence is beyond the Carlos Chipola theory of intelligence, which I love talking about, which is just about how much you're able to help yourself and other people at the same time. So on that note, I will move on to some of the more specific questions. Someone asked about repeating versus non-repeating patterns. So they say from page 35, when I start talking about patterns, for repeating patterns, would it make sense to talk about two objects given that they are identical? I think I know what you mean. I think maybe you mean that if you have a repeating pattern such as, well, look, there's a repeating pattern right here on the piano keyboard. Ta-da, here's a repeating pattern. And does it make sense to talk about two objects? So if two notes have the same pattern in this situation, does it make sense to talk about them as different? And I think that, well, as usual, there's a sense in which we can and a sense in which we can't, because I just pointed at two F sharps. And they are both F sharps, so they are the same note in the sense that they are both F sharps, but they were F sharps at a different point in the keyboard, so they were different F sharps in different octaves. So they were both the same and different. And so I suppose there is a sense in which it makes sense, and there's a sense in which it makes sense to call them different, and a sense in which it makes sense to call them the same. And this is something that really confused me basically all the way through my undergraduate degree until I met category theory, because I met things like the group with two elements. So there is only one possible group with two elements, but we can call them different things, and then they're different. And I kept getting really confused about whether that meant that there were different groups with two elements or whether they were all the same, because we kept seeming to say that there was only one possible one. And so now I know that what that means is that there is only one up to isomorphism. And I just wish I'd had the language to say that when I was an undergraduate. But I do now. And so now I feel more confident in saying, well, here's a sense in which these two things are the same and a sense in which they're different. And then the question goes on to have a part about non-repeating patterns. So I think what this question means, and I may be wrong, but I'm trying to use some of my psychic powers here. I think what this question means is there are some patterns which consist of something like a tile repeating itself, like the picture I gave, or the repeating, I'm leaning the wrong way, the repeating patterns on the piano keyboard. And then there are some patterns which are more of a similarity between different situations, where we go, I'm seeing a pattern here among behaviors of people, for example. And maybe there is a sense in which both of those things count as a repeating pattern. It's just that one of them is repeating right next to itself in space, and the other one is repeating at a greater distance. But maybe in some sense, a pattern is always something that is happening more than one time in different places, or at least different abstract places. So it could be at different times. And so maybe a pattern simply is a similarity between two different things, at least two different things that are happening. I'll have a little sip of wine on that. What? The next question is about multiples of 3. This is relating to page 36, and it's about the patterns I made for multiples on grids. And so I said that the multiples of 3 make a more complicated pattern on a 10 by 10 grid, or in a, oh, right, no, I'm talking about the ending digits on multiples of 3 in base 10. So it goes 3, 6, 9, 12, 15. You can't see a pattern in the ending digits. Whereas multiples of 5, the ending digits are only 5 or 0. And so the question is, would multiples of 3 be nicer if we were doing arithmetic in base 6 or in base 3? And that's a great question. And you have correctly observed that that would indeed be the case. So for example, if we were doing base 3 is where we're only using 3 digits. So supposing those digits are 0, 1, and 2, that means that the usual number 1 is represented by a 1, and the usual number 2 is represented by a 2. But the usual number 3, we now move into the 3s column. So our columns now, instead of being 1s, 10s, 100s, and 1000s, the columns are going to be 1s, 3s, 9s, 27s, and so on. So the number 3 will come out as 1, 0. And then the number 4 will be 1, 1, and the number 5 will be 1, 2, and then the number 6 will be 2, 0, because it's got 2 3s and then no units. And so in this case, all the multiples of 3 will have an ending digit of 0. And if we do multiples, if we did base 6, then we would go all the way up to 6 before we get an ending digit of 0. So in base 6, every multiple of 6 will have an ending digit of 0. And every multiple of 3, so it's analogous to the multiples of 5 in base 10, where the multiples of 5 alternate between 5 and 0 as their ending digit. So in base 6, I believe that the multiples of 3 will alternate between 3 and 0 as their ending digit. And so yes, the patterns are very dependent on what base we're in. And if the number that we're thinking about has a good relationship with the base that we're thinking about, then the patterns will come out better. Yes, thank you for that question. Someone asks, on page 42, can we think of abstract structures like we do data compression? Well, I had an idea of what that meant, so I looked it up, and it does seem, I think, that we can, that data compression is about restructuring data in order to take up less space. And I think that I would say that in some sense, there is a sense in which finding abstract structures in pure mathematics is like that, because it's about putting things in a structure or recognizing a structure in order to get them to take up less space in our brain, maybe. And I think it's maybe a bit different because it's less concrete. And so we're not sort of physically restructuring the ideas, but what we're doing is we're viewing them in a different way. And it's very possible that we are literally physically restructuring our brain while we do that. Oh, there's a thought. Because thinking is just about things in our brain moving around, right? And holding things in our brain is just about laying down layers of protein on our nerve endings or brain cell endings, I think. So perhaps in that sense, we are literally restructuring something. But consciously, I think what we're doing is we're regarding things according to a different structure, and thereby we are enabling ourselves to take up less space in our brain. Yes, I think that's an interesting analogy. Thank you. The next question, the next two questions are about page 43 and about the analogy arguments I made, where there are two tactics, one where two people are talking about whether two things are, so the argument is about whether two things are analogous, and there's a kind of fork diagram where there's arrows pointing down, and we can use this level to say that they're analogous, or we can go up higher and willfully go too high and then include ridiculous things, or we can go lower and refuse to include things. And someone asked if all slippery slope arguments consist of going higher and therefore including ridiculous quantities of things. And I think I would hesitate to say all, because it's always a bit sketchy saying all, because then you really have to make sure it's all. But I think that sounds very plausible, that many slippery slope arguments are about that. Someone may be able to think of one that isn't. I'm not sure if it's all of them, but I think that's a good start. And the next part of the question is there a sense in which tactic 1 is dual to tactic 2? A question about duals. Interesting. We haven't, the chapter about duals is miles away, but duals in category theory are when you regard all the arrows in your category as just pointing the other way. And it's remarkable how much extra information that gives us. And it also tells us a sense in which some things are part of the same concept. And I think that this, yes, it could be a dual situation. I have actually not tried to make this argument very rigorous, but it is possible that there is a category of analogy arguments where the ones that are higher than the others have an arrow pointing to the ones that are lower down than the others. I mean, they really do have an arrow, and it sort of looks awfully like a category spans, if you know what that is, and even if you don't know what that is. But I feel I won't take the time to explain that now, because that's for way down the line. But I think that there kind of is an arrow pointing down from the higher level abstraction to the lower one. And if we took the dual, that would mean we would just make all the arrows point up in those diagrams instead. And then one of the faulty arguments is going backwards up an arrow, and one is going forwards down an arrow. And then if we took the duals and turned all the arrows around, that would flip. So I think maybe that is a dual. Very good, thank you. And finally, the last question, still about page 43. Do you ever see examples of disputes that might fall a bit outside these two diagram scenarios? Yes, absolutely. There are loads of ways of having arguments that don't fall into those, unfortunately. One that I immediately think of is a straw person argument, where you just replace someone's argument with something else entirely and claim that that's what they're arguing, and then you say that their argument is ridiculous. And indeed, that argument is ridiculous. It's just that that's not the argument they were making. Another kind of argument that would not fall into one of those scenarios is the kind where you just tell someone they're being irrational. I hate those ones. Because if you think someone is being irrational, first of all, it's really patronizing. And secondly, I think if you think someone is being irrational, what you are doing is you are failing to empathize with them enough to understand what their logic is. Because there is always a logic, it's just maybe not the same as your one, and maybe it's starting from different starting points, and maybe their starting point is that their feelings are the most important thing of all. But that's not irrational, that's just that's just starting with a different axiom. So I don't think that that argument falls into one of those either. And I think there are plenty of other arguments that disputes that don't fall into that category. Like if two people simply have different starting points as axioms, for example, if they each believe in a different religion, that's just having a different starting point, and that doesn't fall into that kind of argument either. So that's a kind of, I'm now tempted to sit down and see if I can classify all possible disagreements between people. Interesting thoughts. I'm very happy to have been inspired to interesting thoughts by your questions. So thank you for sending very interesting questions. And that's all the questions that we have today. We have a few nice comments at the end. Someone says they're excited about the book club. enjoyed the first installment and we'll have questions for later chapters. And someone else said, thank you kindly for talking our questions through with us. You are very welcome. And please do, if you would like, spread the word. I would love for many, many people to join in. There's deliberately a long build up before we get to the technicalities. And so I'm hoping that people will be able to jump in, even if they've missed the first few weeks. So do encourage anyone you know of to join in, and do keep sending in your very interesting questions. And whatever day it is that you happen to be watching this, I hope that you are having a better day than I had today. And anyway, cheers, bye.